move on to the next slide, just to kind of set the stage. Something that you probably remember seeing in the news back in 2013 about an asteroid that impacted over Chelyabinsk, Russia. And sorry, I guess I side of the speed, or there we go. Okay. And it was, it was about a 20-meter sized asteroid in size, the prediction or the estimate. It obviously released a lot of energy in the atmosphere on the way in as it disintegrated, did not reach the ground intact. The atmosphere, our atmosphere does a really good job protecting us, but it's very rare. This was like maybe a once a century type event for something that large to enter the atmosphere. You probably heard this past week about fireballs over Ohio and Texas, which is kind of unusual. We get that a lot, and often it's over the ocean and nobody even sees it, but that's like maybe a meter or two in size, something really small. This was still kind of small as asteroids go, but as you see the people running there, well, I don't have the sound in this, but the shock wave from the disintegration of that asteroid in the atmosphere blew out windows. There were injuries from glass, as you saw, knocking people down. From like these different cameras, the sound, again, we heard that this past week with like people reporting a big boom from a fireball in Ohio, and this was quite a boom. And again, this isn't even an asteroid that, even though it caused some damage, at least this is something that, is rare. Our atmosphere does a good job protecting us. We'd like to find out about these, but also the ones that are larger that could do more damage should they impact. So we can move to the next slide, Stacy. Thank you. And so this animation just kind of shows how, kind of being a part of being empowered to find asteroids over the decades, how we found more and more asteroids. 2009, this is what we knew about the solar system. 2018, this is what we knew. I need to update this even more, but a lot of those stay safely out in the main asteroid belt, and you see all those yellow ones out between Mars and Jupiter, but look at all those other ones flying around. Those blue ones are the ones whose orbits bring them into Earth's neighborhood. It looks really busy and messy. Thankfully, these dots are a lot bigger than the asteroids actually are. And so it's sobering to realize, all this stuff is flying out there in space, but space is large, and the odds of something coming into contact with something else that's very the odds are very slim. It's a very rare thing, but it can happen, and it's all physics. We're going around the sun. The asteroids are going around the sun. If we can find these and observe them, we can get information on their orbits and predict where they're going to be in the future. So next slide, please. And so, as I said, I'm representing the Planetary Defense Coordination Office at NASA. We're part of the Planetary Science Division at NASA headquarters. And Stacy said she's from the Solar System Exploration Division out at Goddard. This is kind of applied planetary science as we look at solar system science, what we know about objects in the solar system, but then actually doing something with it to maybe prevent a natural disaster. So this is applied science, and we're bringing science to bear on an actual hazard to Earth. Next slide. I will say for any Star Trek fans that our shield there, if you're a Star Trek fan, Michael Okuda, who did a lot of the graphic design for the Star Trek series, a number of them, he did this for us. So it's very cool, especially for me as a big Star Trek fan. I love it. And so this graphic here just kind of gives an overview of the activities that we do at NASA for planetary defense, and kind of clockwise. First, kind of the bread and butter, the meat and potatoes. You can't do anything about asteroids if you don't find them first. And so search, detect, and track. We fund observatories that use telescopes to survey the skies at night, look for kind of those moving points of light against those fixed points of light, the stars, and then taking that to and following those points of light and turning those into orbits to be able to figure out where are they going to be in the future. Characterize, being able to study properties of asteroids, because if an asteroid were to impact, what its physical properties would help predict, what kind of impact hazard would it be? What kind of damage could it do? And using telescopes, optical, infrared, and even radar, like you see that dish there. Planning and coordinating, we don't go it alone. So asteroid impacts, it's something that it could affect it affects the whole world, and you never know where something could happen. So planning and coordinating, working with other agencies within the U.S. government, but then also working with our international collaborators on addressing the asteroid impact hazard. Mitigation, you probably heard a few years back about the DART mission, Double Asteroid Redirection Test, actually smashing into an asteroid to change its motion in space, as a test, just to see if we had to do this for real, could we do it? Because if you knew far enough ahead of time about a possible asteroid impact with the Earth, if you could deflect it early, you wouldn't have to move it a lot for it to miss the Earth in the future. Mitigation also involves, say we had a case where we couldn't deflect an asteroid, being able to make all the predictions about what the damage could be informs emergency response. And so NASA has that role as playing, being the bringer of information about the asteroid. And then assessing where we're at and continuing that whole process. Next slide, please. And here's just a quick example of like their survey telescopes. These are the ones that find the asteroids, and then we fund a number of other telescopes that then continue to track them, because you can picture like looking up at the sky and seeing something moving across the sky, turning those two-dimensional observations into a three-dimensional orbit. It doesn't help to just see it once. You got to see the asteroid a number of times to be able to really understand how it's moving. And our big producers are Pan-STARRS and the Catalina Sky Survey of the University of Hawaii and University of Arizona. They're in the middle of the plot, producing a lot of the discoveries worldwide, the bulk of them. We also fund the Atlas survey, which is there on the left. It has multiple telescopes that survey the sky quickly, kind of complementing those other surveys that are trying to go after the fainter objects. You've probably heard it's made some significant discoveries, like the interstellar comet 3I Atlas, named after Atlas, and also other comet atlases, and even one of the most significant asteroid potential threats to Earth in the last 20 years. And so it's been very productive. We also collaborate with U.S. Space Force on their space surveillance telescope on the right there, and working with a project at MIT Lincoln Labs to pull natural object data out of the telescopes. And so keeping that going to search the skies every night. Next slide, please. And so here's an example of the kind of the system at work, in a case that, wasn't a problem, but sort of demonstrated and gave us confidence in, that we've got some good capabilities and we can trust, the predictions that we're getting from them. So this was in September of 2024. There were observations. In fact, let me go to the next slide. This is the orbit of this small asteroid that was discovered. And so what happened there on the left were the discovery images of this asteroid. This was, I believe it was the Catalina Sky Survey that discovered it. And so you can see that moving point of light across the starry background. And based on like some of the initial observations, the orbit was calculated. We have a team out at the Center for Near-Earth Object Studies at the Jet Propulsion Laboratory. They take observations by our survey telescopes that are submitted to the Minor Planet Center, which is like the clearinghouse for all of this information on small body positions. They're just routine operations. Well, they predicted an impact. And in the middle there, the top, that was where it was predicted where that impact could happen. This was a tiny asteroid, it was predicted just to be, I think, a couple meters in size, kind of like what came in over Ohio. Nothing that was a hazard, but still, it's kind of cool science too. And so the telescopes around the world continued to track it. And with more data, it was possible to narrow down where that impact could happen. And then it was finally narrowed down to just off the coast of Luzon, off the Philippines. And then sure enough, I mean, again, this wasn't a hazard. So in the next slide, we could kind of have fun with it. And all our data are public anyway, but we put out on social media that, hey, this is going to happen. If you go look there, you might see something. And sure enough, somebody went outside in the Philippines there and looked there, and they captured that fireball. And so again, this happens, the Earth gets hit by stuff, our atmosphere takes care of it. But to actually be able to make that prediction, it shows, our systems are working and we get to do cool science. It's only been about a dozen times that an asteroid has been discovered in space before impacting the Earth. And thankfully, it's the small stuff. There's more of it out there. That's what usually hits us. These aren't the asteroids we're worried about, but it's a good test of the system. So next slide. So now, so that's kind of like practice. Here's what we've been practicing for. And you probably heard about this in the news this past year. At the very end of 2024, this asteroid was discovered by one of the Atlas telescopes, the one in Chile. This was asteroid 2024 YR4 was its designation. And soon after it was discovered, those discovery images there again, that moving point of light, and then continued observations, it was predicted that, it has a chance of impacting the Earth in 2032, on December 22nd, 2032. And as more observations came in, that probability was going up. And so we knew we need to keep an eye on this and see what's happening here, because we actually at NASA have a responsibility to officially notify through the US government if there's a certain threshold crossed for a potential impact in the future, and also notify to our international colleagues, particularly to the UN Office of Outer Space Affairs, to disseminate that information. What this shows here is based on what we knew in early 2025. This is where the asteroid could be on December 22nd, 2032. Any one of those yellow dots. This was a model, based on what we knew. There was a large uncertainty. It could have been way, way, way off the Earth, but the Earth was in the middle of that. And until we knew more, we had to plan on the fact that, there could potentially be an impact with the Earth. Let's move to the next slide as I remind myself what I had there. There we go. Okay, so what happened over time is, as we got more observations in 2025, tracking it across the sky, where it could possibly be in 2032 was shrinking. And that made the probability go up until all of a sudden that uncertainty region shrunk off the Earth altogether, and then the probability dropped. But we didn't know it was going to do it until it did that. And so it doesn't sound like a lot. 3.1% at the end of February last year, before it dropped altogether. I mean, who worries about 3.1%? This was an asteroid that was about 60 meters in size, and I told you Chelyabinsk was 20 meters. This was 60 meters. It's still not, this wouldn't have like regional or global consequences, but it could still be a very bad day for wherever it might impact. Wanted to take it seriously, and it's rare for something of that size to reach such an impact threshold. And so we thought we would go through our careers maybe and not ever have to do like a notification like what we did. But at least, again, the system worked. As observers continued, we were eventually able to say, it's not going to hit. And then the asteroid wasn't observable anymore. And as you see, it kind of shrunk down. It actually shrunk down around where the moon was. And we kind of sat there this past kind of half, 3/4 of a year with the knowledge that there was this remaining 4.3% chance that it could impact the moon in 2032. Now, at least it's not the Earth. And we could kind of think of cool science applications and all that. But it's kind of the situation we didn't want to be in for the Earth, where we had this long period of time where we would not be able to find, or we would not be able to observe the asteroid again, and that's all we would know. A few percent chance of impact, and that's all we know. And this is the sort of thing we work through. We work through different asteroid scenarios. We have exercises. We look at, what would we do in these situations? And then now we were actually living it. Well, at least we didn't face it with the Earth. We were facing it with the moon. Let's move to the next slide. And so what happened, actually, you might have heard just recently, just earlier this month, this asteroid really wasn't going to be observable again. It has this orbit that takes it way out beyond the orbit of Mars. We weren't going to be able to see it. But the folks who had used the James Webb Space Telescope earlier in 2025, they realized, you know what? We could maybe push the capabilities and not have to wait until 2028 to see this again. And so they took that challenge, and they were able to observe 2024 YR4 again. That allowed the people who do the orbit determination to extend the orbit further, to refine it, and that shrunk the uncertainty region off the moon altogether. So now we know it's going to make a close approach to the moon in 2032, but it's not going to hit. We know it that well. And so this was a good test of the system. And we just lived this and went through it. But you know what? We still haven't found all the asteroids that are out there that could come into Earth's neighborhood. And so we still keep on with it. Next slide. And so what do? We find something that has a significant chance of impacting Earth in the future, and then we want to do something. That's what DART was about, testing. Okay, it's all physics. Can we impact an asteroid and change its motion in space and actually kind of have control over our futures, be able to do something about this? But everything changes with trying to do something with a real asteroid with real physical properties and orbits around, as we play tag with asteroids around the sun and all that, and launch opportunities. So this was very successful to do DART. And let's go to the next slide, because I think it kind of shows. Oh yeah, here we go. This is cool, because this showed the launch of DART.
6, 5, 4, 3, 2, 1, and liftoff of the Falcon 9 and DART on NASA's first planetary defense test to intentionally crash into an asteroid.
It doesn't sound right to say we're going to go smash, a very expensive spacecraft, but it had a mission and it did it well. Next slide. And so the goal was actually to smash into a smaller asteroid of a binary system, one asteroid going around another, because it's a lot easier to measure the change in motion of one asteroid around another rather than like an asteroid around the sun on a much larger orbit. And so the DART spacecraft was launched. It impacted the asteroid. Before it did so, it released an Italian CubeSat called Lucia Cube, which took images as it went by. But by changing the speed of the asteroid, it dropped it into a little different orbit with a different orbital period, and it actually changed the orbital period by like half an hour. And so, and that was observed from the Earth, even though you still see a point of light from the Earth, but because you have this binary asteroid going in front of and behind, you see the amount of light going up and down as they do that dance, and that up and down of the light changed, and that's how we knew that, okay, this was a success, and also radar measurements. So the next slide. This is cool because these are the approach images from the spacecraft sped up. And this spacecraft, it had to be able to do some autonomous navigation. It's like, okay, you've got one job. You've got to hit the asteroid, but you've got to hit the right asteroid. You don't want to hit that big one there that we're passing first. You got to hit the other asteroid, and you've got to know to point at the right one. And it ended up working really well. It's also a reminder that, ideally, we'd love to do reconnaissance of an asteroid first, because this was the first time we ever saw this asteroid, and then boom. And you can see this asteroid was very rocky. And there's the last image. This is everybody was cheering that no more data was coming. It was sad. We lost the spacecraft, but it was because this was a success. It impacted the asteroid successfully, and the deflection was measured. Next slide. Okay, so great, but we need to find asteroids. And some are light, and it might be hard to see, but some are very darkly colored. This shows asteroids at the same size, but different color and different reflectivities look very different. But if you could turn on infrared eyes, they can't hide so much. Here again, asteroids are the same size, but different coloring, not reflect. That one on the right does not reflect a lot of sunlight. And if you're looking in the visible, it might be hard to see, but if you could look in the infrared, the coloring doesn't matter, and you can really get more of a handle on the size. So at the next slide, this is NASA's next mission for planetary defense, called the Near Earth Object Surveyor, or NEO Surveyor. I like this slide, detect to protect. But right now they're working towards launching in September of 2027 to and this is an infrared space telescope, and it's targeted for planetary defense. It's going to survey from space, like along Earth's orbit, in front and behind, catching the asteroids that come close to Earth's orbit, because those are really the ones that we want to keep an eye on, but also with the ability to survey closer to the direction of the sun than is possible from the ground. And so very complementary to the ground-based telescopes, looking in the infrared so that these darker objects, it's harder for them to hide, more sensitive to the size because it's looking at heat, it's looking at in the infrared. So it's going to be very powerful and will help speed up finding these asteroids. We actually have NASA has a tasking from Congress to find the asteroids that could pose a hazard to Earth, and in particular the larger ones that are 140 meters and larger in size. And this will help us speed that up to be able to meet our congressional tasking and do this job that we love doing, just retiring the hazard to Earth one asteroid at a time. Next slide. And then finally, we also, if you have an interest in finding out more about what we do, there is a documentary called Planetary Defenders that's on NASA's YouTube channel, and it's also on the NASA Plus app to be able to stream. And it gives a sampling of all of these different things that I highlighted and some of the people behind it, what we do to make this all work. And the next slide, I think, has the trailer there, so let's show that.
Potentially hazardous asteroids can show up anywhere in the night sky at any time. Oh, this might be something. Oh, you guys, look at that. Right now, it is absolutely a potentially hazardous object. If you guys were going to be here for a discovery, a PHA is definitely what you want. Yeah. This is a big rock, yeah.
What would an asteroid that is a kilometer in diameter, what would it do if it hit the Earth?
That is likely to end human civilization.
Those objects are big enough to cause what we would call truly global devastation, meaning that they could cause global extinction events. The good news is that we found more than about 95% of them. When we get down to smaller objects, things that are larger than, let's say, about 100 meters across or so, now the picture's not so rosy.
Today, we do not have a complete inventory of all the possible impactors.
There's almost certainly a decent-sized asteroid out there that is going to pose an impact threat to the planet. We're just trying to find it right now.
And that is something that NASA and the worldwide planetary defense community has been endeavoring to do.
There's a huge community of astronomers that start observing it.
From all around the globe.
Finding asteroids, tracking them, calculating their orbits.
Asteroids don't care about international boundaries.
It doesn't matter where the asteroid impacts. It affects, the entire humanity, in fact, anything alive on the Earth.
I really like that I'm protecting the planet.
Let's say we do find something that poses an impact threat to Earth. What next?
The day is coming when Earth will get impacted.
The dinosaurs went extinct because they didn't have a space program. We do have one.
We can. So why stop there?
We know it will happen. We just don't know when it will happen.
All right. Yeah, it's true. Asteroid impacts have happened through Earth's history, and they'll happen again. Thankfully, it's very, very rare, especially for something of a size that can do damage. But again, we're empowered that we've got the capability to look for asteroids and to make predictions and to react. And so we're carrying that out at NASA and with our international collaborators. So I think that's my last slide. Okay, here's want to leave this up for a second. If you want to learn more, we have our links to our website, the Planetary Defense website at nasa.gov, and also the Planetary Defenders video. And then we've got our link there to the DART mission, because that's what a lot of folks get excited about. So anyway, and so with that, I'd be happy to take questions then, Stacy.